We've worked out the pressure as a function of altitude in a gas, air, and now we'll work out the pressure as a function of depth in a liquid, water. So here in this diagram, I'm showing the air in yellow everywhere and the water in blue. And we'll also look at the interface between these two fluids where they're coming in contact with each other. The first thing to notice about the water in this strangely shaped set of containers connected by this tubing is that the top level of the water is at the same altitude in all parts of the system. Even though our containers are different shapes and different sizes, as long as it's one connected fluid, the top level will be at the same altitude everywhere. Now, the surrounding air has a pressure we know that'll be about 1 atmosphere, and we know that it decreases slightly as we go up, but the decrease is slight and we'll be neglecting it here. So in the picture below, I'm showing with these red ones that we have approximately 1 atmosphere of pressure in all of these cubes of air surrounding our container full of liquid. So right at the surface of the liquid, pressing down on the liquid, will be 1 atmosphere of pressure. And then by Newton's third law, if the gas is pressing down on the liquid here, then the liquid is pushing back up on the gas. That is, this cube of water here is responsible for holding up this entire column of air, extending up to space. So the forces that they exert on each other will be equal and opposite. So the forces per unit area that they exert on each other will be equal and opposite, indicating that the pressure at the top level of the water equals the pressure at the bottom level of the gas. So the water pressure here at the surface will be 1 atmosphere, matching the pressure of the gas that it is in contact with. So now we know that the pressure at the top of the water is 1 atmosphere. Let's see how it increases as we go deeper into the water. And we'll be looking at these 3 fluid elements here, these 3 water cubes that I've colored purple, pink, and reddish. So first, the free body diagram for that purplish cube of water right there at the surface. There'll be a force from the air pushing down on it, and call that F5 since it's the force exerted at an altitude of 5 meters above the ground. There'll be a force upwards on that cube from the cube of water below it, pushing up on it. That's F4, since it's due to the pressure at an altitude of 4 meters above our reference point. And of course, there's a force of gravity due to the weight of all of the H2O molecules in that cube. Now, we know that the difference in pressure between these 2 levels here is given by this expression. The density of the water in that fluid element times little g, which will still approximate as about 10 newtons per kilogram, and then the height of that fluid element, which will be a meter. This is a cubic meter of water right there. So the density of water is about 1,000, well, exactly 1,000 kilograms per cubic meter. So I've already done some canceling of units here. Kilograms cancels kilograms. This meter cancels one of those meters cubed to make meters squared, leaving us with newtons per square meter of pressure. That's the SI unit, which is equivalent to a Pascal. So this is 10 to the 4th, 10,000 pascals, which is equivalent to 1/10 of an atmosphere. So we've shown the pressure difference between top and bottom of this 1 meter tall fluid element is 1/10 of an atmosphere. So then if the pressure here is 1 atmosphere, matching the gas that's above it, then the pressure a meter down into the water will be 1 plus that 1/10, so 1.1 atmospheres when we're a meter deep. Now let's go deeper. To compare the pressure at levels 3 and 5, that is to find the pressure down here 2 meters deep into the water, we'll use our same formula. The pressure difference between these 2 locations, 3 meters and 5 meters, the pressure difference is given by rho GH. Rho, the density of the fluid there. So here we're kind of looking at this stack of 2 fluid elements together, the density of that water, times little g, times the height of that combined fluid element, treating these 2 cubes as 1. So a total height of 2 meters between these two positions. So then that calculation is going to give us twice as much as our previous calculation. That'll come out to be 2 times 10 to the 4th pascals, or 0.2 atmospheres. So the pressure difference between these two locations is 0.2 of an atmosphere. Therefore, the pressure at level 3 here is equal to the pressure there, 1 atmosphere, plus an extra 0.2, so 1.2 atmospheres. And now we see the pattern with the pressure increasing by 0.1 atmospheres for each meter of depth we go into the water. So we could express this as an equation for the pressure as a function of depth in a liquid. D will be the depth below the surface. So the pressure at some depth is equal to the pressure at the surface plus this term, rho g times the depth. This gives the pressure as a linear function of depth here. Graphed, it would be a line with a slope of rho g, which would look like this here. Pressure as a function of depth. So at the surface, the pressure matches the pressure of the gas that's above it, and then the pressure increases linearly with depth, the slope there being that rho g term. It depends on the density of the liquid and the planet that you're on. So our picture here showing the gas pressure and liquid pressure. We've got gas pressures that are basically the same in all these locations, changing very little with altitude. But the water pressure, indicated by this axis over here, increases as we go deeper into the tank, starting at 1 atmosphere at the surface level, matching the gas above, and then increasing by a tenth of an atmosphere for every meter of depth, going down to 1.1, 1.2, 1.3, 1.4, 1.5 atmospheres once we are 5 meters deep in the water. What about these points like B, C, and E, which are inside these tubes that don't have gas directly above them? I want to make a quick argument about the pressures at those locations. So back to the 3 specific fluid elements from before. Now here I have a horizontal axis, x in meters. And if we look at the forces, the horizontal forces now on this pink fluid element, there is a force pushing it to the right from this cube over here, pushing our pink cube to the right. We'll call that F2. It will be the force due to the pressure at position 2 here. And then there's also a force pushing the pink cube to the left that's coming from this reddish cube there. And those two forces have to cancel if our element is in hydrostatic equilibrium. So the force at position 3 must be equal to the force at position 2. Furthermore, if we look to the right at this cube here, this reddish cube, and the forces on it, it'll be pushed to the left by this cube here with a force we'll call F4 being exerted at position 4. And this cube will be pushed to the right by the pink cube. We'll call that F3, the same F3 as we've got right here. And again, those forces have to balance. So we're arguing that F2 must be the same size as F3, must be the same size as F4. And so all those forces per unit area must be equal as well, indicating that the pressures are equal. The point is that the pressures will be the same as we move along any horizontal line. Same pressure as we move horizontally so that the forces balance. Therefore, coming back up to this picture, if A, B, and C are all on one horizontal line, then the pressure at A equals the pressure at B equals the pressure at C. And it looks like it'll be about midway between these two marks, so about 1.25 atmospheres of pressure at those 3 points. If we go down, then the pressure increases, but as we go horizontally, the pressure stays the same. So the pressures at D and E will be the same, looks like about 1.45 atmospheres. So there's our conclusion. Stated as a principle, in hydrostatic equilibrium, pressure is the same at all points in a fluid along any horizontal line. And we'll use that principle as the basis for a good deal of our problem solving. final note here, to compare our conclusions about pressure in a gas and pressure in a liquid, we recognize that the very gradual decrease in pressure with altitude in a gas versus the very rapid increase in pressure with depth in a liquid is ultimately due to the differences in density between the two materials. Water being 1,000 times more dense than air results in the increase in pressure with 1 meter depth of water is 1,000 times greater than the decrease in pressure with 1 meter increase in altitude in the air. It's 0.1 ATMs is 1,000 times greater than 0.0001 ATMs in the gas.